All right, so hopefully you finish writing these down, but hopefully what we're gonna see today is that we're working with rational functions. We're going back to the beginning of the semester when we were talking about making sure you know what type of equation you're solving, right? None of that changes. What about these tells us that we have rational involved? It doesn't have to have exponents in the denominator, but the key is we have a fraction, right? These fractions do have polynomials in the numerator and denominator. This one can be written in that same way as two, but it's just written in a different form. The key is though, is whenever you have that variable in the denominator, right? So make sure you see here, once we have a variable in the denominator, now we have a rational function. Okay, so we want to keep that in mind. With that said, as we deal with rational functions, that's going to be kind of a place of focus. Start there, right? So with polynomials, we do need to look at things like, hey, guess what? The degrees will still matter as we deal with these functions. Right? As you can see here, the first, all of those have leading coefficients. We could still talk about that, but for the rational exponent, we need to make sure to set in place, hey, there's some restrictions involved, right? Just like I said on when we did the equations, right? Set up your restrictions first and then move forward. We want to take that same pattern. Now, hopefully what you took from yesterday as we looked at some of these graphs is that those restrictions impact how the graph looks, right? So this one had 2 restrictions and I had 3 separate lines when I went and graphed it. The first one we did had 1 restriction, right? Ended up having 2 separate lines. Now, today we're going to focus on those vertical asymptotes, right? When we move forward, though, we'll talk more about the horizontal asymptote as we deal with stuff, okay? With that said, though, what is the restriction for this function here, f? The denominator is x plus 3 squared, right? So all we need to say is x plus 3, x plus 3 cannot be 0. Do I need to write the squared part? No, that just means both factors are exactly the same, right? That's what the squared means. So remember multiplicity, that's just what we call multiplicity. This is multiplicity. That's going to impact the graph. And we'll look at that more as we go through over the next week. It does impact the graph. But for our sake, hey, x plus 3 is the focus, right, for the restriction. Well, that means we can't use negative 3. Right? So how do we write the domain when we can't use a specific number? That becomes the one thing we do need to remember. So what did someone write? Parentheses, right? We don't want to use any of that, right?
And then the union.
Mm-hmm.
And then negative 3 to negative.
All right. Why are these so important? What does that tell us we're using still? Still all real numbers, right? Make sure you see here, it's all real numbers such that we're just not using the negative 3. Okay, if you remember when we kind of talked about this, another great way to write that, it's x is an element of the real numbers such that, I don't remember that symbol, x cannot be negative 3. Okay. The key is whether you write it in this form or you write it with this form, we need to be saying, hey, I can use any real number, just not negative 3. Okay. Any questions where we're coming from with that? Now, is there anything we can do to simplify f of x when we look at this? So everyone's saying there's not really much. We could technically do the subtraction, but that's not going to change the denominator. All right. So with that said, what can we call this situation here when I look at the graph? Okay. And this is where we're going to start to say, hey, my restriction can take on different forms, right? There's 2 main things that you're going to look for here. The situation where you can't simplify and we're just stuck with the x plus 3 in the denominator. And then there's going to be times where you can simplify, right? So whenever you can't simplify out that factor, That's when you're going to conclude that, hey, we have a vertical asymptote at that value. All right, I can't use it. It's not a part of the graph. That's where we come in and call it an asymptote. And it does not like my handwriting. All right, are we good with where we're coming from that? So if I were to go start a graph, that's an important piece that we would want to use, right? That, hey, when I go draw this graph, the very first thing I'm going to do is draw it. And I remember yesterday I talked about, I like to use dotted lines or dashed lines, whatever you want to call it. My graph is going to be somehow situated around this. Okay. That's why it's important to get to it right away. Now, as far as collecting points, that's where the next step comes in and with finding intercepts, right? Intercepts, as we saw, polynomials was important. It's going to be the same thing here. So let's make sure we're comfortable with that process, right? So hopefully what you're seeing here is we can definitely go find a y-intercept where we'll have what, 2 minus 1 over 3 squared, which is what, 1 over 9. So if we do all that, we're going to end up getting 17 over 9. So you use your calculator again to work that out. Just make sure you see 3 squared is 9. That's why we have a denominator of 9 now. 2 times 9 is 18. So that's where I got the 17 from, because 18 minus 1 is 17. With that said, though, that's almost 2, but not quite 2. So we could use that as a point to plot, right? Just remember I put it on the y-axis, though, because that is our y-intercept. Any concerns there? All right, so the next step, though, is our x-intercepts. What's going on here, though, we have to be careful of. It's the squared will be something we have to watch out for, right? Is this in the form that we saw yesterday? What's different about f of x when we compare these three that we have to make sure we watch for? Both of these are just the fraction, right, by itself. A single fraction. Is this just a single term, though? One fraction by itself? No, right? This is where we see that, hey, I had something go on here to give me a 2 on the outside. All right, one of the things we're going to talk about with rationals is that you can actually do the division sometimes and rewrite the function in this form, right? This would be a good example from if we wanted to, we could go do the division and see what happens. Doesn't always help you, but that's something that we could talk about. With that said, when I deal with this function here, when you set it equal to 0, you have to acknowledge that 2. And the way to acknowledge that 2 is by making sure you isolate the terms themselves. So as you see here, I added the fraction to both sides. What would be minus? Well, you could subtract 2 from both sides, but I added the fraction to both sides.
Oh.
Since the fraction was negative, I just moved that over to make it positive.
I got confused with that. I thought you.
I just moved the fraction because since it was negative, I can make it positive. Now, with solving this here, it's still the multiplication, right? I can multiply both sides by my denominator to solve. What you're going to find here is that would give us 2 times x plus 3 squared equal to 1. I can then divide both sides by 2. All right, and then what would I do here to finish solving? That's where our square root comes in, right? Now, should I even bother do the square root here, by the way? What am I looking at before I do a square root? So like when I get here, what am I watching for before I put the square root? What is it that square roots can get mixed with that would say, hey, I don't really need this right now? What type of numbers are we using? Real numbers, right? If this was -1/2 and I do the square root of it, it's now what? Imaginary. Do I want that right now? No. So keep that in mind. Always watch that as you're dealing with this. We saw this with polynomials. Guess what? It can come up with rationals anytime, right? We should expect quadratics all the time when solving. Okay. So make sure you see here though, when you do that square root, I'm okay dealing with that. Give us x plus 3 plus or minus, equal to plus or minus the square root of 1/2. Now, the proper way to write that, remember, is to get that 2 out of the denominator so that it's a perfect square. So you multiply top and bottom by 2. And the reason we like that is because 2 times 2 is 4. And what's the square root of 4? 2. So that'll give us x equal to -3 plus or minus the square root of 2 all over 2. It's called rationalizing denominator. I think it's easier to do it here than waiting this step. Okay. But the whole idea there is I don't have a square root in the denominator. The square root of 2 is in the numerator. That's the main thing. With that said, though, those are our 2 intercepts. But what does that -3 mean to us? When we see kind of some symmetry in a sense, right? It's not quadratic symmetry, but hey, I can go to the right of -3 and the left of -3. Why is the -3 significant to us in this moment? What does that -3 come from? It's our restriction, right? Isn't that kind of like I mentioned before, almost the center of our graph in a sense? Now, what you'll find here is if we did go and look at the graph, remember that it's x plus 3 squared, so that's going to impact how the graph looks. But there's going to possibly be some symmetry here we're going to see as well, okay? Now, things that we're going to move forward to then is to talk about how this 2 impacts the graph, because that 2 is very important. If you remember, this 3 here will be a shift to the left 3, and because that's a positive 2, it's a shift up 2. What's the reflection mean again? Well, the negative is a reflection, right? So we still have transformations here that we could use to help us graph this, okay? The key then would be making sure you go back and look at, okay, what does 1 over x squared look like? Okay. Well, if you take what we learned for polynomials, that means both sides, both edges better be the same, right? Well, both sides of the asymptote, what you're going to see there, will both be doing the same thing. Okay. Now we'll go into further detail with that at a later time. I just wanted to make sure kind of introduce why this function would be nice from a graphing standpoint. Okay. Finding the intercept, I had to do a little bit more work than we probably wanted to with the whole square property, but that was because of how it was situated when we started. So the last thing I would say about this problem is always make sure you pay attention to the way it is set up. Okay. Whereas we go to this next one, this is where we see, as someone mentioned, a polynomial over a polynomial. Okay. What should I try to do to polynomials when I have polynomials? Factor, right? Now, the thing is when I go do my restrictions, I'm going to have to factor anyways, or try to, right? We may not always be able to solve by factoring. We might have to do the quadratic formula, but we should still try to factor anyways. And what I recommend is just always factor the whole thing at one time, because you're going to need to at some point, right? So make sure you remember from the restriction standpoint, we're going to need to factor. When you deal with x-intercepts, remember that numerator is going to be what we set equal to 0 eventually, and we're going to need to factor that, okay? The big difference was don't do that for this one. It didn't have one fraction by itself. Remember that 2 changed everything. That's why we had to do something different here. Okay. But since this is just one fraction by itself, I'm going to use that numerator later as well. So it's better to just factor it from the beginning. Okay. So with that said, what's special about the numerator we do need to recognize? How do we know that? It's been a little while since we've done this, but this was one of the ones I said we need to know, right? We have x what? Not squared, cubed, right? So what is special about 8 when we think about cubes? All right, so 2 cubed is 8, right? So guess what? This is a situation where we need to go back and remember that a cubed minus b cubed can be factored to a minus b, a squared plus ab plus b squared. If you remember, that's where the word SOAP came in to help us remember what we were doing here as well. Same, opposite, always positive. Okay. So that would give us, in this case, x minus 2 times x squared plus 2x plus 4. Now, am I going to be able to factor this any further? No, that's why we have the formula. And what we should expect here is if I ask you to solve it, that it's going to be complex. All right. We go with that formula. Now, what's nice about the denominator, though? Right, it's a trinomial, right? So a times c is 5. What factors of 5 add to 6? All right. So 5 and 1 work well here. So that'll give us, in the end, whatever method you like to use, make sure you see here, get x plus 5 and x plus 1. With that said, can I simplify this fraction at all? All right, there's nothing in common, right? I did all that, and this is the best I'm going to do. But remember, even if you can't simplify, it's going to help you with other parts of this problem. I asked you to identify the domains, and you're going to want the denominator for the restrictions. So we have that set up nicely now. You want to find intercepts, so the numerator being factored helps you with x-intercepts. So understand that doing that from the front end, you're helping yourself out because you're going to need it anyways. Okay. So with that said, though, this is going to give us the restrictions that we need. So we can go over here and state those. That x cannot be -5 or -1. Now remember, this is the domain that does get a little bit more burdensome to have to write out. Not x. Just make sure you put the smaller number first, and do not forget your middle interval. Okay, so -5 needs to go first, and don't forget that -5 to -1. Any concerns where we're coming from with that? I know we didn't do a lot with those on the second part of our test, right? You remember for test 2 and stuff, but that was something we needed to be comfortable with. That when you talking about this, that's where that formula came in that we talked about just now. You have to go back to that formula that I had written down. That's the way to get it. You can do synthetic division now too, right? Let me stop there. Another way to get that is synthetic division. If you don't believe me, go do the synthetic division. You would do plus or minus 1, 2, 4, and 8, and you can do that. And this is what you'll get. But make sure you see only one number is going to work. So as you go through all that, the only thing that would work would be +2. Okay, so it's much more convenient to remember this. Are we good though with where the domain's coming from? Some of y'all need to drink some coffee before you come to class. That was what I felt like today. All right, we're not done yet though. What should I call those restrictions now since I could not simplify? Right? Since we could not simplify, right, those will be vertical asymptotes. And what we'll see here, like if I compare this back to what we did here, this is what our graph's going to end up looking something like this. Not exactly, but there's going to be some similarities here. Okay. So make sure you see, like, as you compare this one, I had 3 parts to my graph. 1, 2, 3. Well, that's because I had 2 restrictions that became vertical asymptotes, right? So that's what we're able to do here is say, hey, these are going to be the 2 things that break up my graph. What's the next thing I've been asked to do though? We got our domain. We've identified the asymptotes, so let's find the intercepts, right? Now, remember, as someone mentioned, that no, since these are both polynomials, the y-intercept is still nice. Just remember, though, it's a rational function, right? So you're going to see the fraction that's formed from those constant terms. It's still the constant terms, but we have a fraction because it's a rational function, right? Now, make sure on the test, am I expecting perfection when graphing a fraction? What did I say when I did this one real quick, right? 17/9 is almost what? Almost 2. It's just below 2. So as long as you're just below 2, we're fine. Does everyone follow that? With that said here, -8/5 is what? 1.5 almost, a little bit more than 1.5. So just make sure you're a little bit more than -1.5 downwards. Okay. Now, as far as the x-intercepts are concerned, make sure you see here that we're taking our function and we're setting equal to 0. But since you already factored it, as long as you remember to do that, you've done a lot of the work already. We know that one of our x-intercepts then is going to be x equal to 2. Right? The next thing then is to look at the x squared plus 2x plus 4. Now, you're not able to factor that. We know that because of the formula perspective. So the next thing to do would be to jump into the quadratic formula. But remember, as I kind of talked about in equations, it's been a little while. We haven't necessarily directly talked about it. I mentioned it with graphs, but more briefly. But with the equation side, if you look at the discriminant, the part that's under the square root, right? Remember, it's -b plus or minus the square root of this b squared minus 4ac. Do a quick check. This will give us 2 squared minus 4 times 1 times 4. So 4 minus 16 gives us -12. Should I continue working with that? Where is that -12 going to be? Right, remember it's -b plus or minus this situation, right? This is what is under the square root. So that means this is going to give me results that are not real. So make sure you take something here and say not real and don't do the whole thing. Now, if I told you to find the zeros of the function, yes, give me all of them. But this is where you save yourself time. Now, if you're going to forget, find all of them every time and only take real numbers. It's better to find them and then not to. Okay. But if you remember, this is a great way to save yourself some work. Hey, I'm going to have to do b squared minus 4ac anyways, so let me do it first. If it becomes positive, hey, you just did the work already, plug it in with the work that you did already. Don't start all over again because you already did it. Is that clear to everyone? Because from here, you could be like, hey, this is x equal to -2 plus or minus the square root of -12 all over 2. You saved yourself a couple steps of writing all this other stuff with it. Does everyone see that? But what I like about it, if I see this on your test, that means that you're catching on that, hey, my focus here is real numbers. So this is the part that would determine if it's real or not. Okay, do we follow that or any concerns with that? All right. My main thing is then is nothing's wrong with imaginary numbers. We, for graphing's sake, so we focus on real numbers. Okay. So as far as this is concerned, we had our y-intercept, which we found here. And now we have one x-intercept is what we found here. Okay, so is there anything I could clear up here for somebody? And as we mentioned, remember the formula, but if you forget, you're going to be doing synthetic division. The synthetic division definitely will work. It'll just take you longer. That's why it's better to remember the formula. Okay. Is there anything I can help someone feel better about here? All right. So here's the next one. Hopefully you see it's very similar setup, but there's going to be something that's a little bit different about this one. Okay. Now, as far as the factoring is concerned, make sure you see that first one is going to be -20 and -8. So we can use 2 and 10. 2 and 10 work nicely here. Just make sure you use -10 and +2. So whatever factor you're comfortable with there, that'll give us these factors though. All right. If you like the factor by grouping approach again, please fill it in. We don't have time to do factor by grouping every time now. Okay. But this is what tells me it can be factored, right? And as far as the factors are concerned, what's 5 times -2? Isn't that the -10 I just said to use? And then 2 times x is going to be the +2 that I mentioned, right? So those numbers are still there as well. What's special about this, the denominator though, that we have to remember? Difference of squares, right? So let's make sure we write that out. X plus 2, x minus 2. Okay. And what should I state now? My restrictions. Don't do anything yet. Hopefully you caught something going on, right? But make sure you state your restrictions first. All right. Once you factor, state your restrictions. Okay. With that stated now, what's going on though with my factors? All right. Aren't these exactly the same? Can't I divide them out to 1? Now, be careful here that you saw I stated my restriction first. Then I need to move forward and say, hey, h of x can be written in a simpler form, which will make it nicer to work with in the long run. This will definitely help us out as far as something that's a little bit nicer to work with, okay? But that restriction is still important because it still impacts the domain. This was my original function, not this. That's just a simplified version of it, okay? So when you do your domain, you still need to make sure to include both the -2 and the +2. Sorry, let me say that correctly. Exclude both the 2 and the -2. Do not use them, okay? Now what you're gonna find here, we're gonna graph this function, and then we have to make an adjustment to account for that 2. All right, that's what we end up doing. We end up graphing that function, then we just like, hey, we'll make that adjustment later. The way that we make that adjustment though is with how we describe what happens, right? Remember, if you can't simplify something, that's a vertical asymptote. So the factor that was left over is this x plus 2. I could not simplify that, right? So one thing that we do need to make note of is, hey, we have a vertical asymptote at x equal to -2. All right. The x equal to +2, we need to do an adjustment ourselves. So what do we use in a graph to show that we cannot use a particular point? Open circle, right? So if I take a line and I have to cut it and put an open circle here, what's a simple word we can use that we just did to that line? We put what in it? If I used a nice little punching tool, I could have put a punch in there to open up a gap in that graph. We wouldn't call it a punch though, we'd call it a what? Or I could look at, you could, simpler way, fold your paper in half and cut out that point. It would form a hole, right? So mathematically, the open circle we'll call a hole. We're cutting that out of our graph. That's why we call it a hole. But understand that's going to represent a very specific point, okay? So what we need to do then is make sure as you state this, when you cross this out, write the word hole as you do it. Because then you'll come down here and say, hey, I don't have a vertical asymptote at 2, but I have a hole, not halo, hole at x equals 2. All right. Now, this is one of those things that it doesn't come up all the time, right? If you can simplify, understand that that's a unique situation. It doesn't happen all the time, okay? But it happened here. Does everyone understand where I'm coming from with that? The difference between when I can't simplify versus when I can simplify? And how we're going to call the one where we can't simplify a vertical asymptote, but the other one we're going to call a hole? Now, make sure again that just kind of describe it. We might have something that looks like this. We're simply saying, hey, I can't use this. So the way that we mathematically show that is we put a hole in the graph by drawing the open circle. Okay, that's where we're coming from. Now, with that said, are we done with this problem? We need to find the intercepts, right? Now, let's check something. Does the intercepts change from the original function to the simplified function? Right? That's something that we do need to look at. So if I look at this and I say, what's h of 0? Is -4/4 -4 the same as 2/2? Are those the same? Yeah, it's kind of nice, right? That, hey, I can go in there and say, hey, that's still +1. So the nice thing about this is we can use the simplified version for this part. So like when I go over here and say, hey, find h of x equal to 0, just use the simplified version. All right, what did I leave off though when I wrote that equation just now? The x plus 2, right? Because the denominator, that's where the vertical asymptote came from. We already dealt with the denominator, right? Now we're focused on the numerator. So we'll get -2/5. Subtract the 2, divide by 5. Okay. Now, some hints there, know that your hole's probably going to be somewhere. It's still, sorry, your hole is still going to be at that x minus 2 that we lost. That's still a part of what we're dealing with. Sorry. That's what I'm trying to say. Questions or concerns? I can't tell if we're glazed over, if we're just done with the semester this week, whatever it is, I can't tell. All of y'all went out and partied last night, is what it is, huh? Rain or not, huh? Are we okay with the idea of, me looking at the denominator in a factored form still? As we look at all three of these, having that factored form in place? I know that like here, I wasn't trying to get to the polynomial aspect, right? But the fact that these are all going to involve polynomials in one way or another, that factored form is still important. Make sure you see here, I just happen to put this one in that what we'd call a kind of a graphing by transformations form, right? That's what this one's nice for. So if I ask you to graph that, we can kind of use those shifts and reflection as I mentioned. That's why we like this form. But we should expect things to be more in this general form as we deal with stuff, okay? Now, with that said, though, are we okay with the difference between a vertical asymptote and a hole and where those come from? Hopefully you're catching on, though. This goes back to why I said make sure we state our restrictions first on the equations, right? Because, hey, guess what? We needed it for the domain. And here we're expanding upon that domain, right? So we started with restrictions. We gave the domain a reference, like I can't use that. How do we write it? This is where this fun statement comes in, right? But please keep in mind, the x not equal to is still saying the same thing. Okay, so when you get on the test, at the very least, tell me what x can't be. Show me that you did this to get this, right? This is part of that, right? That's the mathematical notation that we're practicing to use. But that is not the end result. That's just an interpretation. So please keep that in mind. With that said, our first direction is vertical asymptote, right? Start by calling it a vertical asymptote, but what changes that? What happened here that said not a vertical asymptote, but a hole? Right? Once you're able to divide it out, right? That's the key. Once you're able to divide it out, that's why I said make a habit of just writing hole there when you do it. So you remind yourself, hey, it's still a restriction, but it's not a vertical asymptote, it's just a hole. I just need to go draw my graph and erase a quick piece of it and put that open circle there, okay? That's how we want to interpret that. Any questions I can clear up then as we deal with these, we're finishing up for today. I never extended that due date, did I? No one told me. All right, let me shut off this real quick.